So, good afternoon, students, and happy New Year to all of you. Okay. So, this is our first class in the new year, and we have already completed with the parametric tests. And in parametric tests, we have done Z test, T test, chi-square test, F test. Okay, and then we have also taken up the analysis of variance. So now we will be moving on to the end of these tests, and there will be two topics left in this statistics. That is, one is known parametric test, and other is experimental designs. So we will be completing this in 2-3 classes. So I think I will be devoting one or two sessions to these non-parametric tests, and one session will go for this your experimental design. Okay, experimental design is just a basic concept, and there you will be refreshing your knowledge of NOVA. So I just request you all to just go through the lecture of ANOVA before we going for this your experimental design chapter. Okay. So today let us start with the known parametric tests. Okay. So you have been introduced to the general class of testing of hypothesis, and whatever these testing of hypothesis up till now we were doing, these tests, popularly known as parametric test, assumes that parameters okay, such as mean, standard deviation, okay, etc. exist, and they are used to develop a test, right? That is, whatever test we have done, you have seen that we had made a use of mean and standard deviation or variance. For example, a t-test is based on the comparison of means of two tests, right? The parametric tests which we have studied earlier are developed with an assumption that the form of population distribution was known, right? That is, from which population you have taken your sample, its distribution pattern is known, and that a test concerning a parameter of distribution was to be made. That is based on that distribution, whether it is a normal variate distribution, or it is a t distribution, chi-square distribution, or f distribution. Accordingly, we devised a test and tested our hypothesis. Okay. So, test of hypothesis which deal with the population parameters are called as parametric test. If you are testing a hypothesis which deal with the population parameters, right, which deals with the population parameters, is known as parametric tests. But there are situations, particularly in psychological and market research studies, also in our this clinical studies, wherein the basic assumption underlying the parametric tests are not valid, or one does not have the knowledge of the distribution. What happens if you does not have this knowledge of the distribution of the population, right? That is to be tested. Then what you will do? So these tests which handle the problem of these type of known as known parametric tests, and they are also known as distribution free tests. So many a times this definition is being asked, what are known parametric tests and what are parametric tests. So known parametric tests are one, which are distribution free tests, and in these the knowledge of the distribution of population parameter is not necessary. Okay. So in the recent past, the known parametric tests have gained importance basically because of three reasons. One is, these tests require no or less restricting assumptions than the corresponding parametric test. If you are going to apply a parametric test, then you ought to have some restrictions or assumptions on which the test can be applied. But it is not so in case of non-parametric tests. Second is that these tests are more suitable for analyzing ranked, scaled, or rated data. That is, if you have nominal data or frequency data or ranking, then you can apply these tests very well. Then third thing is that these tests involve very few arithmetic computations. That is, there are less of computation are required in case of these known parametric tests, and that is why these tests are gaining very importance now, right? So now, however, it must be understood that when basic assumption about the parametric test are valid, the known parametric tests are less powerful. It is not like that you have all the basic assumptions available, even then you go for non-parametric test. You must go for the parametric test because the known parametric tests are less powerful than parametric tests, right? So thus, there is a greater risk of accepting a false hypothesis and thus committing a type 2 error. That is, known parametric tests are more inclined towards the type 2. Secondly, in non-parametric method, the null hypothesis is somewhat loosely defined, right? That is, thereby, when the null hypothesis is rejected, the known parametric test yields less precise conclusion compared to the parametric test. For example, in parametric test, we have a test for equality of two population means, t-test, say for example, compared to the two population distributions are identical in a non-parametric test. So in non-parametric test, actually you are testing that the two population you are testing whether they have same type of distribution or not. That is, they go for the identicalness of the distribution rather than some parameter like mean or standard deviation. They look for the distribution in the data, right? So they generally test the distribution, right? So in this case, a rejection of null hypothesis in a parametric test would mean that the two population means are not equal, while the rejection of null hypothesis in a non-parametric test lead to the conclusion that the two population distributions are different. We simply get an idea that the two population on which this known parametric test has been applied, their distribution is different. That's all, right? So the specific form of these differences between the two distribution is not clearly specified in known parametric. Oh, okay. So the following are some of the typical situations for using non-parametric test, right? What are these situations? Say for example, in a consumer behavior survey for new package design, the responses are likely to be normally distributed but clustering around two extreme positions, with a very few respondents giving a neutral response to the package design, right? So in the middle you will not get much responses, either will be on the one side and others will be on the other side, so you will not be getting normally distributed, right? So in such situation you have to go for the known parameter. Sometimes the response to a question are given in terms of names, right? That is nominal data, right? So which cannot be treated as numbers, right? So for example, if we ask young graduates in which part of the country you would like to take up a job and live, so their reply will not be like that 10 or 12 or 15. It will rather be that they would love to work in north, northwest, west or south or particular city, the name of that city. So such a data which cannot be treated as number, that nominal data can only be analyzed using the non-parametric methods, right? So second thing is, that is when it is not when your data is not normally distributed, right? One thing, then you have to apply the non-parametric test, and if it is in nominal data, then also you go for the non-parametric methods. Then in a mailed questionnaire methods of survey, more often partially filled questionnaires are received, and non-parametric tests are designed to take the omission data and make necessary adjustment to extract maximum information available from the data. So when you are having missing data, then these nominal or these non-parametric method of testing will be rather better as compared to your parametric, right? Then non-parametric test can be used to provide reasonably good results even with very small samples, right? So in case of parametric test, it is always better to have a large sample and then test. But in case of non-parametric test, even on the very small samples, you can apply non-parametric tests. Okay? So now these non-parametric tests can be divided into one sample test, two sample test, and k sample test. So today we will be trying to do this one sample tests, right? And then in the next session of this non-parametric test, we will complete with the. So let us see how much we will be completing. Okay. So let us start with the first one. That is the one sample test, right? So the one sample test are used to answer questions such as, is there a significant difference between the observed and expected frequencies? Okay. So such questions are being answered by this one sample test. Is it reasonable to believe that a sample has been drawn from a specified population? That is, you are comparing the distribution of the sample with that of the population. Then, is it reasonable to accept that the sample is a random sample from some known population? That whether that sample you have taken, is it random or is it deliberately been taken particularly from some respondents? So, these type of things can be tested using the one sample non-parametric tests, right? So, and one more thing in non-parametric test, their pronunciation is very difficult, most of the test. Because if you see the parametric test, you have Z test, T test, F test, and then this chi-square test, okay. Chi-square test is the one test which is applied in the parametric as well as non-parametric, right? But most of the non-parametric tests, they are quite difficult to pronounce, right? So let us see and start with the first test, and that is Kolmogorov Smirnov one sample test. Okay, so I will just call it KS test. KS one sample test. So this I will write it here. This is KS. Otherwise, it is very difficult to pronounce every time. So this test is used for comparing the distribution on an ordinal scale. Say for example, your data is in ordinal scale. So that particularly, that is in the rank form. So this test particularly tests the distribution on ordinal scale. The test is concerned with the degree of agreement between the distribution of observed value and some specified theoretical distribution. So what we will be doing, we will be seeing that whatever values has been given to us, okay. So the distribution of those given values or observed values, whether they have the agreement with some specified theoretical distribution, so that theoretical distribution we have to provide from our side, right? So it determines whether the scores in a sample can reasonably be thought to have came from the population having the theoretical distribution. So we will try to understand this with an example. So what is that? Say for example, a leading paint manufacturer is interested in developing a new color shade, right? So he is interested in testing four different shades. Let it be any color, and in that the shades are dark, bright, light, and very light. Now, a sample of 160 customers were shown these four shades, and the following results were obtained. That is 30 like the dark shade, 45 like the bright shade, 60 like the light shade, and the remaining like the very light shade. Right? So the manufacturer wants to know whether the sample results indicate any preference towards any of the shade. Right? So this is what we want to know from this data. So what will be the solution? So we will be applying the KS test, right? KS one sample test. And how to apply that? So the test procedure to test the above hypothesis involves specifying the cumulative frequency distribution. What we will be doing here? We will be specifying the cumulative frequency distribution. Cumulative frequency you all know. and then I will show you in the table that how to make this cumulative frequency distribution. So which would occur given the theoretical distribution under hypothesis H, and comparing that with the observed, that is what we will be observing and what is theoretical, we will be comparing these two things. So right, so the point at which these two distributions show the greatest absolute difference, so what we will be looking at is the greatest absolute difference between the what is observed and what is theoretical, that has to be determined, right? Now, reference to the sampling distribution would indicate whether such a difference is likely to be on the basis of chance or whether it is there, right? So, the case test assume that the distribution of the variable being tested is continuous as specified by the cumulative frequency distribution. So its statistics is given by D is equal to maximum of this F naught X is the observed one, and this one is a sample, right? Where F naught X is the theoretical cumulative frequency. This F naught X will be your theoretical cumulative frequency distribution under null hypothesis, and your SNX will be your observed cumulative frequency distribution with a sample size of L, right? So statistical table given below gives the critical value of D. So I have given this table for case test. Say for example, you have N, that is this is the sample size. So this is the table. It has been up to 40, and if the sample size is greater than 40, then we apply the formula like at a different level of significance. That is, it can be 0.2, 0.1, it can be 5%, 2%, or 1% level of significance. This gives you alpha. So, say for example, if I want to see at the 5% level of significance and my sample size is say for example 10, then your this table value will be 0.409, right? So, whatever the D value we will be getting from here, that we have to compare with the critical value, right? And if the calculated value of D exceeds this value, the null hypothesis is rejected, right? If you will be calculating the D and that will exceeds the your table value, then your null hypothesis is rejected, right? So let us see that how this will work with an example. So above question, what we were having, we have observed number of customers, that is 30 were liking dark, then 45 were liking bright, then 60 were liking light, and 25 were liking very light. Now we have to make the cumulative frequency, right? So what will be cumulative frequency? 30, 30 plus 45 is 75, then 75 plus 60 is 135, 135 plus 25 is 160. If you divide this 30 with 160, so this will give you the SNX, that is the observed cumulative distribution, that is 0.1875. This will give 75 by 160, this will give you 0.4688. That is, if you divide this 75 divided by 160, so it will give you 0.4688. Similarly, you will find this value, that is 135 divided by 160, this will give this, and 160 divided by 160 will give you 1, right? So this is our observed cumulative distribution. So if there might not have been any difference in the differences are not by chance. So every shade should be liked by equal number of participants. So 25 will like dark, 25 will like bright, 25 will like light, 25 will like very light. So this will make our theoretical cumulative distribution. So it will become 0.25, add 0.25 to it 0.50, then add 0.25 it becomes 0.75, and at last it becomes 1, right? Now we will be finding the difference between this F naught X and this SNX. So F naught X minus SNX, so this difference, that is 0.25, 0.25 minus 0.1875, it will be equal to 0.0625. So it has been written here, right? So this 0.5 minus 0.4688, it will be 0.0312. This minus this, it is absolute. This you also see. This value is absolute. Although this will be in minus, but we have converted the sign into plus, right? And then this 1 minus 1 is 0. Now, out of these four values, we have to look for the maximum value. And what is that maximum value? Maximum value of this f naught x minus snx is 0.0938. So your d maximum is equal to 0.0938. So here this n is equal to greater than 40. So from the table we have to apply this 1.36 upon root n. So it will become 1.36 upon root n table value at 5% level of significance. It will become 0.1075. Since the calculated value of t, that is 0.0938, is less than the critical value at 5% level of significance, the null hypothesis is accepted. That is, it is not rejected. And that is, any difference in the shade, preferred reference is only due to chance, right? So whatever the differences in these values, instead of 25, 25, 25, 25, you are seeing 30, 45, 60 and 25. It is only due to chance. It is not it is not a significant difference. It does not deviate significantly from the normal distribution. That is the theoretical cumulative. So this is how you apply the KS one sample test. Okay. Now we will be taking up this runs test for randomness. So that completes our KS one sample test. Now we will be looking with this second test, and that is runs test for randomness. What is runs test of randomness? In order to draw conclusion about the population on the basis of the sample information, it is necessary that the sample drawn must be random or unbiased, right? Isn't it? That is, when we are drawing a sample from a population, that it is a prerequisite that it should be unbiased, right? The run test is used to test the sample for randomness. Okay, if you want to test that the sample which you have selected is random or not, then you can apply runs test. So the test is based on the order or sequence in which the individual observations originally were obtained. Okay, that is, it works on the order or sequence. So a run is defined as a sequence of identical symbols or elements which are followed and succeeded by different type of symbols, right? That is, sequence of identical symbol or elements, those are followed and succeeded by different type of symbols or elements. So this is our criteria. So say for example, in studying the arrival pattern of customer in a large departmental store, we might observe the following sequence of male and female arrivals. That is, first male come, then female, 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 then male come, then three female come, then male came. So for this sample of 20 customer, we can observe that there are 9 runs. How we can calculate that? So all males together, then all females together, then male, then female, then all males together, one female separate, these males separate, these female separate, and male separate. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So in total, in these 20 observations, there are 9 runs. This is how we calculate the number of runs, right? Now, the total number of runs in a sample is an indication of whether or not the sample is random or not, right? Too few runs or too many runs indicate lack of independence or known randomness. That if there are too few runs or too many runs, these both indicates lack of randomness, non-randomness. So, in order to use the run test, we observe the sequence of occurrence, right? So, whatever the event we are having, n1 plus n2 is equal to n events, total n events, and determine the number of runs r, as we have discussed here. So here number of male and females will be, number of males will be n1, number of females will be n2, and both will constitute total number of observation 20, and number of runs we have calculated 9. Okay, like that. So if both n1 and n2 are equal to or less than 20, then we use the statistical table. If n1 n2, that is male female, are either equal to or less than 20, then we can use this table. Which table? So I will just click and make you see. This is available online, so I will just increase the font. Okay, so what you can see is that on the two sides there are, these are the up to 20 values are there, right? And one is n1, other is n2. So given in the table are various critical values of r for values m and n less than or equal to 20 for the one sample run test. Any observed value of r which is less than or equal to the smaller value or is greater than or equal to the larger value in the pair is significant at alpha 5%, right? Say for example you have 5 on this side and 7 on this side, so it will be 3. So anything if your r value come out to be less than 3 or greater than 11, then it is 3, right? So we will be doing one question so you will better understand. But if your n1, either n1 or n2 is larger than 20, we use normal distribution as the approximation to sampling distribution. In that case, the mean runs will be equal to this formula, and your standard deviation of runs will be equal to this formula. Okay, and your z statistics will be calculated by run minus mean of the run divided by standard deviation of the run, right? Once you got this z value, you can compare this with the standard z, right? This is how run test is applied. So let us do one example. Okay, so here what is that? If the normal probability table is used to obtain the critical value of z, and the hypothesis h naught is rejected when the calculated value is greater than the critical value. If your calculated value comes out to be greater than the critical value, then you reject the null hypothesis, right? So in order to study the arrival pattern of a customers at supermarket, the manager noted down the arrival sequence of customers sex wise, male and uh, man and woman, right? And the sequence is like this. Okay, now I have already divided them in the form of runs. So there are, how many runs are there? If we calculate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. Now, in order to conclude the randomness of the arrival pattern of customer, we can use the run test. So our null hypothesis will be the arrival pattern sex wise of the customer at the supermarket is random, and that of the null alternative hypothesis was that it is not random or non-random. So here we have this men 23, woman 27, and the number of runs as 24. Okay, that is we have calculated. Now mean run, that is expectation of R, will be given by the formula I have already told you. So this mean value came out to be 25.8, and this standard deviation will be given by this formula. Okay, so when we calculate this, we put all the values into it, the standard deviation came out to be 3.48. So your z value will be this r minus er, that is z, absolute z will be equal to r minus er upon standard deviation of r. So when we put all these things, so it came out to be 0.52. So at alpha at 0.05, the critical value of z is 1.96. As the calculated value of z is less than the critical value, the null hypothesis is accepted. Therefore, the whatever persons are coming over there are coming at rank. Okay. So this is how we apply the runs test. Now comes your another, this is the, I think, last test, not last, second last test. And this test is known as sign test in one sample test. So all tests concerning means that you have studied are based on the assumption that the samples are taken from the population having roughly the shape of a normal distribution. Okay. Then this assumption is untenable. That is, your population is not following the normal distribution. The standard test can be replaced by a non-parametric test, and this is known as sign test. So one sample sign test is applicable when the sample is taken from a continuous symmetrical population. That is, you do not have that bell-shaped curve. It is symmetrical population. Everything is same. So in this case, the probability that the sample value is less than the mean and the probability of sample value greater than the mean are both 1 by, okay. So this is we know theoretically, right? Both are 1 by 2. Any sample value, whether it is less than mean will be 1 by 2, greater than mean it will be 1 by 2. Suppose we are testing our null hypothesis that our sample mean is equal to the population mean against a suitable alternative hypothesis using a sample of size. So the procedure adopted in sign test is very simple. And what is that procedure? Each sample value greater than mu naught is replaced by a plus sign. Any sample value that is greater than your population mean is replaced by a plus sign, and those less than is replaced by a negative sign, right? Then we then test the null hypothesis is that the plus and minus signs are the values of random variable having a binomial distribution with p is equal to 1 by 2. In case any sample value exactly equals mu naught, we simply omit it. So for example, for a small sample, the test is performed by computing the binomial probabilities, and for a large sample, it can be calculated by the approximation to the binomial distribution. So we will see both. Okay. So first example is, say for example, it is desired to test the hypothesis that a median value mu of a continuous distribution is 15 against the alternative hypothesis that it is greater than 15. Okay. So 20 observations were taken and the following results were obtained. So these are the 20 observations. And now we have to see that whether it is median value is 15 or greater than 15. So it is has to be done at the point that is 5% level of significance. So just what we will do, that replacing each value greater than 15 with a plus sign and that with the less than 15 with a minus sign we get. These are the plus and the minus sign we will be getting. Now the question is whether there, then we will calculate how many plus signs are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 plus signs are observed in 20 trials, support the null hypothesis p is equal to 1 by 2, right? So we can find what we will be doing. Here we will be using the make use of the your binomial distribution. So we can find that for n is equal to 20 and p is equal to 1 by 2, the probability of 14 or more successes is 0.05. And since this is less than or equal to this alpha 0.05, we reject the null hypothesis. Therefore, the median value of the distribution is greater than 50, right? So this is how we do this sign test. Then here we can also use the approximation to the normal distribution that we will see in this example. Okay. So say for example, a data given below is on the large industrial plant daily emission of sulfur oxide in tons. Okay. So a large plant is there and this is the sulfur oxide emission. So use the one sample sign test to test the null hypothesis that the plant's true average daily emission of sulfur oxide is 23.5. And its alternative is that it is less than 23.5. So what we got is we have 11 plus signs, so we will replace these things with the plus and minus signs. So what we will be getting for 23.5, we will be getting around 11 plus signs and 29 minus signs. So P will be, our hypothesis will be that it is half, and our alternative will be it is less than half. So now for 40, and out of these 11 should be plus or more. So this we can calculate using this Z formula, normal approximation of the binomial distribution. In that, this Z will be equal to, this is X, so NP is your mean, and square root of NPQ is your nothing but the this variance. Variance is NPQ and mean is NP, right? So we will put the values of P and Q here, right? And now I think okay, now we are live. So basically what I was telling is that this Z can be this X minus NP upon root NPQ, where this NP part is this NP part, this particularly this NP part is your mean, and this NPQ is your variance. So I will stop after this because your next class will be there. So this will be equal to this, and finally you got this Z value as minus 2.85. So the absolute value of this is 2.85, and absolute critical value of Z is 1.64 here. So as the calculated value of Z 2.85 is greater than the critical value, the null hypothesis is rejected, and therefore we conclude that the plant's true average daily emission of sulfur dioxide is less than 23.5 and not 23.5, equal to 23.5. So this is how we can apply the sign test. Okay, and from your next class we will be doing our one of the important non-parametric test for one sample test, and that is chi-square test, which is generally being asked in the examination. So this is all from today's class, and as I can see that there is no question in the chat box, so I will be stopping the lecture here, and tomorrow you will be having test, and that test will start at your 10:15. Okay, and it will start at 10:15. There will be what we can do is that we can have a 30-minute test, right? And that 30-minute test you will be having around 25 questions. Okay, so 25 questions you have to do in 30 minutes. Sometime I am giving you, because you have to write your answers in your Google form. Okay, so for filling those answers, and you will be getting your question paper on your mail. Every student will get a separate paper. Okay, so 25 questions in total. I will be giving 5 minutes for filling up the values. Okay, and submitting it. So in total, I will be giving 30 minutes, right? So you will be starting at 10:15 and submitting your paper before 10:45 tomorrow morning. Okay. So good luck to all of you for your first test from the chapter 1, that is introduction and importance of statistics and biostatistics. So some students were having confusion that whether it is unit 1 or chapter 1. It is only chapter 1. That is one chapter will come. Introduction and importance of statistics and biostatistics. And tomorrow we will be starting from, not tomorrow, in the next week I will be taking up from this chi-square test. So thank you very much. Thank you for being with me and for your patience.